Hello, my name is Harshesya from CSPIT IT. Today I am excited to present our project on the Fibonacci series calculator, a digital logic-based system that generates Fibonacci numbers using hardware components. Let's start with the basic. The Fibonacci sequence begins with 0 and 1, and each following number is the sum of the two before it, like 0, 1, 1, 2, 3, 5, 8, and so on. The mathematical formula is Fn is equal to Fn minus 1 plus Fn minus 2. Beyond maths, this sequence appears in nature, architecture, and algorithm, even in computer science. Since our implementation is in digital hardware, we rely heavily on binary addition. Binary digit or bits are only 0 and 1. Here are the basic rule of binary addition is 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 1 is equal to 10, which is 0 with a carry of 1. An example is 101 plus 011 is equal to 1000. This operation form the backbone of digital computing and our Fibonacci calculator. A half adder is a basic circuit that adds two single binary digits A and B. It gives two outputs. Sum is equal to A XOR B. Carry is equal to A and B. While it can add two bits, it doesn't handle carry in, which limits it for chain operation. To handle larger binary number, we use a full adder. It adds three input A, B, and A carry in. The logic is sum is equal to A XOR B XOR carry in. Carry out A and B or carry in, and we can build a full adder using two half adders. This will allow us to sum Fibonacci number properly in hardware. Now, Fibonacci generator, add stage. In our Fibonacci generator, the full adder is key. It takes two previous Fibonacci number, store in binary, and add them. The result is the next Fibonacci number. We discard the carry out bit because we are only interested in the sum. Now the storage register, sir. To store Fibonacci number, we use two registers. One hold Fn minus 1 and other Fn minus 2. These values are added and the sum is stored back into one of the register for the next cycle. We use a clock signal to update. At startup, register are initialized to 0 and 1. Now we see overall block diagram. This slide shows the complete block diagram. Two register feed the full adder. The adder compute the next number. The result loop back into the registers. A clock pulse control when update occurs. A reset button brings the system back to the starting value 0 and 1. So the overall conclusion for the seventh slide is the logic gate in half and full adder register to store Fibonacci value. A scalable architecture. This design is not just theoretical; it useful in real application like digital signal processing. So now we move into the actual circuit level implementation. We use logic gates to construct the adder. Register were built using D flip-flop. We also design control logic to update the system properly and verify it with the simulation. So half adder using XOR and XAND gate, full adder by combining two half adder, ripple carry adder to perform n-bit addition. They form the core of our arithmetic operation. Registers are made from array of D flip-flop. Shift registers allow data movement. Parallel load register enable quick data loading. They help us store manipulate Fibonacci number efficiently. So top level setup includes some steps like first one is register to hold f minus 1 and f n minus 2, and second one is n adder to calculate f n. Third one is control logic to manage update. Fourth one is the n output display. This setup help us iterate and generate the Fibonacci sequence. So we have main three states. First one is reset, initialize the registers. Second one is calculate, perform the addition, and third one is shift, update the value. A clock signal drive the timing, and logic gate manage transition between states. We physically implement this design by writing logical gate registers and control circuit. We include clock and reset the signal routing, power management using capacitor. This gave us a functioning Fibonacci calculator on hardware. Using simulation tool like Vivado, we verify the logic input, clock and reset signal output Fibonacci number at each stages. We track each calculation and result match expected value. So the previous slide's conclusion is we have demonstrated the circuit level design for a Fibonacci calculator. We have also explained adder, register, and control logic implementation. Finally we provide simulation and output verification. So we then took the design to actual hardware. We use a Xenix Architect 7 FPGA running at 50 mHz on chip block RAM for storing value, a 16 into 2 LCD display to sequence, a 5-volt power supply for stable operation. So here mention the four component we described previous slide, uh, in which we use in the hardware. In hardware, we use iterative addition inside to register, a stage machine to control sequence flow, a display driver for LCD output. This setup ran completely on the FPGA. We display the first 10 Fibonacci number from F0 to F9. Each value was shown on the LCD for 2 seconds. Then the next value appears. This gave a smooth sequential visualization of the sequence. Our simulation and hardware run were closely matched, less than 1% difference. Minor discrepancy due to signal delay or clock jitter. This validation validated both the logic and implementation. We faced and overcame a few challenges. The clock speed was limited to 50 mHz due to time constraint. LCD requires sense delay to work correctly. Power noise was reduced with decoupling capacitor. These tweaks ensure reliable performance. So the final conclusion for this is we successfully build a Fibonacci calculator using digital logic. We verify it through simulation and hardware. This FPGA-based design is efficient, flexible, and ready for future enhancement like faster clock or long sequence. So thank you.